Hi, my name is Lisa Elkin. I'm a PhD student at the University of Washington. Today I'm presenting work I did during my master's degree at the University of Waterloo with Jean-Baptiste Beau, Géry Cassier, and my master's advisor Daniel Vogel. Our paper is called Manipulation, Learning, and Recall with Tangible Pen-like Input. Most pieces of software have many different commands that can be selected. Sometimes these are in hierarchical menus that can be frustrating to navigate. Sometimes these take up tons of precious screen real estate, particularly on tablets. And command selection and parameter manipulation are completely decoupled. For example, selecting a pen width and drawing a pen stroke are two completely different actions. And so imagine if instead of selecting commands like this, we selected commands like this. Here, a device is tapped with one edge to select the color purple, and then a thick line is drawn with a corner, color is changed to green, and then medium dots are drawn with a different corner. The idea of this device comes from Vogel and Cassier's work about a device called Conte. They drew inspiration from an artist Conte crayon, which is that stick of coal that artists use where they can draw different lines of different thicknesses depending on how it contacts the paper. And so they asked, what's the digital analog of this device? And if you look at its extruded rectangle shape, if you count up all of the corners and all of the edges and all of the sides, you get 26 different contacts. And so what if you could create a device where you could detect which contact was touching the screen? And that would mean that you could map 26 different commands to each of the 26 contacts. So they built a prototype that used infrared light and a diffuse illumination table, and they used computer vision to classify which contact was touching the screen based on its shape. But because they used shape, they could only distinguish between contacts that looked different, which meant that they couldn't tell which corner was touching, although they could tell that a corner was touching. And this meant that they could only distinguish between 10 different contacts. So their work left some questions unanswered. First of all, how can we actually build this 26 contact prototype that realizes the full vision of this idea that they had? They claim the device would be fast to manipulate, but this isn't tested, and we can make a prototype of many different sizes, and we don't know how size impacts manipulation time. And finally, probably the most burning question is, can anyone learn to use this thing? Can people remember the location of 26 different commands located on spatial landmarks on the outside of a 3D input device? So, our first order of business was to make a prototype that could actually distinguish between 26 different contacts. We wanted it to work on any normal capacitive touch display, like an iPad or a touchscreen laptop. So we made a conductive device, and what that means is that a touchscreen device can't tell the difference between Conte touching the screen and your finger touching the screen. So we 3D printed a case out of PLA plastic, and we covered it in copper tape to make it conductive. Now, designing and 3D printing the endpoints were a little bit trickier. We wanted the corners to feel pen-like, but touchscreens filter out small touches so that random conductive particles in the air don't count as touches. So if we made the corners really pointy, they would be dismissed as noise. So to overcome this, we 3D modeled air pockets into the corners, and we 3D printed them out of squishy conductive material. So they felt pen-like, but when they touched the screen, the air pockets allowed them to expand in surface area, touch the screen with more surface area, so they wouldn't be dismissed as noise. Then we put hardware inside the device. We have an IMU that tells us the angular position of the device, and that is attached to a microcontroller with Wi-Fi capabilities so that those angles can be sent over to a computer. And then there's a small LiPo battery inside the device so that it's completely wireless. Now, we were so proud of our conductive Conte prototype that we took it to the grocery store to weigh it, and we found its weight is comparable to a standard stylus, which is 21 grams, and Conte weighs 25 grams. So we have this IMU data that's sent over from Conte to a computer running software that we wrote. And that software has a decision tree that uses the roll and the pitch of Conte to determine which contact is touching the screen. Then there's a touchscreen device that can be the same device as that computer, but it doesn't have to be, and it sends touch events over to the computer. Now, just like we had to make the corners touch the screen with a large enough surface area that they wouldn't be dismissed as noise, we had to make sure that none of the contacts were so big that they would be dismissed as a palm. So we had to make some interesting design decisions with Conte, and this meant that we had to do some touch smoothing, and we needed to know which contact was touching the screen in order to do the touch smoothing properly. So the software that we wrote takes that touch information, takes the classified contact, does some filtering, and packages it all together in Conte messages, which are down events, up events, move events, and air events. And air events just say the angle that Conte is at. so that the software can use that information when it's not touching the screen if it wants to. And that's all sent back to the touchscreen device so that Conte applications can be interactive. So since Vogel and Cassier were inspired by an artist's crayon, art applications are sort of a natural use case for Conte, but we built a demo to show probably a more widespread use, which is a PDF annotation application. So here, Conte is used with one corner to draw in red, a different corner is used to highlight. And perhaps my favorite part of the demo, we are certifying that this is a Conte demo by using one end to stamp a signature and one end to stamp a date. All right, so we have our conductive 26 contact input device, and now it's time for experiments. So throughout the evolution of Conte, there have been 3 different sizes. Small size, which is the artist Conte crayon, the medium size, which is Vogel and Cassier's prototype, and the large size, which is our conductive Conte prototype. And so we wanted to test the impact of device size on manipulation time. We 3D printed 3 different mock-ups in our small, medium, and large size, and we painted each side with a different color, which we'll explain later. And we also had a pen mock-up, which we also painted different sides with different colors as a baseline comparison. We use the term manipulation to mean when a device is rotated from touching the screen with one contact to touching the screen with another contact and back again. Now, if you count up all of the possible pairs of contacts, it's 26 choose 2, which is hundreds of contacts, and that's not really realistic in any sort of reasonable experiment time. And so in order to mimic real use where a corner would be used as an inking corner, we designated one corner as a start corner, and then all manipulations start from start corner to a different contact and back again. And we use the term manipulation corner to describe the contact in a manipulation that is not start corner. So we built a light box with some light bulbs, a camera at the bottom, and a plexiglass top, and there was this resistive touch sensor on top of the plexiglass. So the resistive touch sensor allowed us to know when a mock-up was touching the screen, and we used the current frame of the camera to classify which contact was touching. Now remember how we painted each side a different color? We measured the relative proportions of each color in the frame when the mock-up was touching the screen to determine which contact was touching the screen. The user was shown 2 images side by side, representing each contact in the manipulation from the user's perspective, and the active contact was highlighted in green, and that just meant that was the contact the user was supposed to touch the screen with next. We had 12 participants, all red-handed, 4 sizes, small, medium, large, and pen. Each participant used all 4 sizes, and size was counterbalanced using a 4x4 Latin square. And then for each participant, for each size, manipulation contact order was random, and they completed all manipulations that started from start corner. And then the task was, for each size, for each participant, they had to complete as many manipulations as were required to complete 2 consecutive error-free manipulations per contact. So our hypothesis was that the smaller devices would be faster to manipulate, and this made sense because contacts on the smaller devices are closer together. So we were quite surprised when we found that the largest device size is fastest. So we found a significant main effect of size on log transform manipulation time, and post-hoc tests found all pairs of sizes to be significantly different from each other, with small being the slowest, then medium, then large being the fastest. We also compared to a pen, and a pen has 5 different contacts: the nib, the barrel, the back, the edge between the nib and the barrel, and the edge between the barrel and the back. And we designated the edge between the nib and the barrel as start corner because that represents a typical inking position. So in order to make a fair comparison between a pen and Conte, we determined 5 contacts on Conte that were similar to the 5 contacts on a pen. And then we compared manipulation times between pen and their corresponding Conte contacts. And we only found 1 pair to actually be slower with Conte. And so this suggests that a pen isn't any faster to manipulate than Conte, and it only has 5 contacts, where Conte has 26. All right, so now we're on to the most burning question, learning. Can anyone learn to use this thing? So we used our conductive Conte prototype to test this, and it only had 3 visual markings. There was a white marking on one end, a white marking on the top, and a white marking on one side. And this was the smallest possible amount of visual information that we could give participants so that they could distinguish different contacts, different edges, and different sides from each other, but it gave them no extra information and didn't tell them what any of the contacts actually did. Because Conte is a 3D spatial interface, which hasn't been studied, we wanted to compare against some baseline, so we compared against a 2D spatial interface. We drew inspiration from Gutmann et al.'s FastTap, which is a grid-based spatial interface in which commands are located in grid cells, and a grid cell is tapped to pick the command, and then it is executed. We also had to have some way to teach people where commands were, and we again drew inspiration from Gutmann et al. With follow-up work that they did on FastTap, where they made a game to teach people commands. So, we mapped 26 toy commands to each of the 26 contacts on Conte, and each toy command had a corresponding icon. So the way the game worked is an icon would fall from the top of the screen to the bottom of the screen, and the user had to execute the corresponding command before it reached the bottom. Now, expert users who had learned throughout this training process where commands were could just execute the command immediately. Novice users were able to open a novice guide after a short delay to find the corresponding command, and then they had to close the novice guide and they could execute it. There was a small penalty in the game to discourage people from using the novice guide, with the hopes that they would become experts by the end of the study. The grid interface works similarly. Commands were located in grid cells, and novice users could open a novice guide, which would show them where the commands were after a short delay, and they could execute the command, but expert users could select the command immediately. And again, there was a small points penalty in the game to encourage people to become experts. We used 26 commands on Conte, we used the same 26 commands on the grid interface, and we also tested a simpler version with 9 commands on one end, and we did this because we thought it might be really difficult to learn the location of 26 commands, and that we might get more meaningful information from 9 commands. We had 32 participants, 6 left-handed, 4 conditions, Conte 26, Conte 9, Grid 26, Grid 9. The study was between subjects with 8 people per condition, and the task was there were 24 training blocks where participants would play the game. Blocks had different speeds, which we elaborate on in the paper, and within one block, each command fell from the top to the bottom in random order. After the 24 training blocks, there were 3 retention blocks, one 0 minutes after, one 10 minutes after, and one 24 hours after, so we could see how many commands participants remembered. During a retention block, each icon matching a command showed up in the middle of the screen exactly once. It didn't move, and participants had as much time as they needed, but the novice guide wasn't allowed, and they were given no feedback about whether or not they selected the right command. So, people can learn to use Conte. After 0 minutes and after 10 minutes, there was no significant effect of condition on recall rate, and all of the recall rates were really high. After 24 hours, there was a significant main effect of condition on recall rate, but post-hoc tests found that only Grid 9 and Grid 26 were significantly different. Now, it's true, Conte 26 didn't beat Grid 26, but we never set out to do better. We thought the grid interface would be much easier to learn than Conte, and we just wanted to measure how much easier it was to learn. So we think that the lack of significant difference is really just due to the fact that all participants were able to learn all of the different conditions, and as you can see, the recall rates for all of them are really high. But we did do a power analysis to see how much of an effect we could have measured, and we have enough statistical power to have found a medium to large effect if one existed. So this says that if there is a difference between Conte and grid, it can only be a small difference. In the paper, we also discussed completion time, expert usage rate, and error rate during the training blocks. In summary, we created a conductive 26-contact Conte device, found larger sizes are faster to manipulate, and people can learn and recall command locations. Thank you so much for watching, and we hope you read our paper.